Okay, in this lecture, we're going to cover the last section. So this was going to be the last lecture. We're going to cover section 5.5. This is on the substitution rule. This is also sometimes called U substitution, and it'll be clear why we call that. We call it by that name once we actually get into working through some examples. Before we get into section 5.5, though, I want to go back to section 3.10, and this is on linear approximation and differentials. This is going to be this idea of a linear approximation is more or less this idea that function is locally linear at a point. That is, it looks like a line, or just I shouldn't say just any function, but a differentiable function. So let me share my screen. So we need to go back to 3.10, as I was saying, because there's some ideas there that we need to make sense. We need to make sense of U substitution, particularly the notion of a differential. So there's not going to be any homework on this. This is just a supplementary section that makes sense of some ideas in section 5.5, which there will be a homework. So linear approximations. Let's talk about these first. We've actually really been talking about them already. So the first part is not going to be anything really new. Linear approximation is the idea that you are locally, a function is locally, function is quote unquote locally linear. And that is it is a line at a given point. It looks very close to the point. It looks like a straight line graph of the function. So for example, you could have something like this. And I can't zoom in much more than this, but you can see that at this point, A, comma FA, this blue dot, you have the graph, which is in blue, looks like a line. Very close to this point right here. This red line, this is the linear approximation. This line it coincides with the graph of the function itself. And of course, as you go further away, say it points over here, then it begins to diverge from the straight line. But very close to it, it looks like a line. And this is actually really helpful for computations, because there will be some functions which are not very easy to compute unless you have a calculator. So you can imagine this idea of linear approximation was useful for calculators. And in fact, I'm pretty certain just that's how calculators work. They do a linear approximation. So when you type in the square root of 3, for example, you're not getting an exact answer. You're getting a decimal approximation. And it's going to use this idea of linear approximation. And the reason why square root, for example, or basically every function we're looking at, is locally linear, that is, it can be approximated by straight lines, is because they're differentiable. So this idea of being locally linear or approximating a function by a linear function is just the idea that our functions are differentiable. So in this case, for example, this is just probably going to be the tangent line. So this right here, this red curve is the tangent line. And so if you start with a differentiable function, then you can, at this point right here, you can take the derivative of the function. The derivative gives you the slope of the tangent line. And so given this point on the curve and its slope, you can plot the tangent line, which will be this red line right here. And very close to it, first of all, the tangent line intersects this point. So they do actually overlap. The tangent line and the curve overlap exactly at this point, A comma F of A. But even very close to it, they're almost overlapping. So it's this line approximates it. So if you're differentiable, then if you're differentiable at a point, then you are locally linear at that point. Your graph looks like a straight line. the graph of the function. And as I said, I can't zoom any further, but you can imagine that if I zoom in on this point, the closer and closer I get, the more indistinguishable the line is from the graph. They just coincide more and more and more. So this will approximate the line will approximate the graph. It's going to approximate this function. So we're just looking at differentiable functions, so we can always talk about these being locally linear. And so if I have a point, I have first of all, I have a function or a curve, and I want to look at the tangent line at this here, I can approximate it. So we're gonna approximate the curve by the tangent line. It's not gonna be exactly equal to it, but it'll be approximately equal to it. So here's the equation of the tangent line. Remember, this is gonna be your slope of your tangent line, and this will be the tangent line through the point A comma f of A. And so you can just give it a name, L of x. So this is gonna be the line linear approximation to the graph at the point A comma f of A. And then you can call this the linearization of the function. So the function itself might not be linear at that point. But it's like you can think about it as this tangent line is the linearization of it, which is like you can approximately treat it as linear. So what you have is that near x equals a, you have that f of x is approximately L of x. They're approximately the same. Or you have this. And this is, again, you have this equation, this approximate equation. This is true for x. No, I don't want to say x equal a, but x just true for x near. Oh, this is completely wrong. Let's say x near a. This is true for x near or close to a. And that just means on some open interval containing a, you have that this equation is true or approximately true. So let's look at this example. Not going to go through a whole lot of examples. I just want to introduce the ideas. So we're going to skip some examples. So we have this square root function, and as I said, this is not easy to compute for certain square roots. I mean, if you have square root of 4, square root of 9, etc., these are easy to compute. They have an exact answer, but square root of 3, square root of 5, etc., these don't have exact answers. So what we want to do is we want to linearize this function. We want to and approximate these numbers right here. So we want to so what we need to do then is we need to find the tangent line to points near 3.98 and 4.05. And I guess what we would choose is just near the tangent line at 4. So we would want to take, oh yeah, so we want to take the linearization at a equals 1. So and when a is equal to 1, we have square root of 4, so it's the function is equal to 2 at that point. And these points right here are close to square root of 1 plus 3, which is equal to square root of 4, which is 2. So these numbers are close to this. So if we can get a linear approximation at a is equal to 1, that line will be able to approximate these numbers here. And we can actually get a good idea as to how close it is, our approximation. But in order to do that, first we need to take a derivative. So this is going to be our function right here. And when you differentiate it using the power rule and the chain rule, you get this right here. So when when x is 1, you get 2, which is what we have up here. And so we have a point, 1, 2, which is on the curve. And now we have the slope. So we plug 1 into here. We get 1/4. So we have point and slope, so we can get the line. So here's the linearization. So L of x is going to be f of 1 plus f prime of 1 times x minus 1. And when you simplify that, you get this. And so what that means is that near 1, when x is near 1, our function, which is square root of x plus 3, is approximately given by this line. This is much easier to compute. we can compute with this line. For certain values of x, for example, when our x is such that we get 3.98 and 4.05 under the square root, these are not going to be easy to compute. However, what we know that since when x is 0.98, you get under the square root point. Let me actually write this out because they're not really being precise here. So what we really want to estimate whoops, are the numbers f of 0.98, which is going to be equal to square root of 3.98, and f of 0.05, I think 105, yes, 5, which is gonna, when you plug it into your function, be square root of 4.05. And so in particular, we have or in particular, we can say since 0.98 and 1.05 are near 1, right? These are numbers very close to them. We can approximate f of 0.98, which is equal to this square root. And we can approximate f of 1.05, which is this square root. And we can just approximate it by plugging it in to our line, because this will be very close to the actual value. And so here's the setup. So here's the square root of x plus 3. It's the blue curve. It looks like this. And then the red line is the tangent line at this point to this curve. And you can see it's very close. So 0.98 might be like right here, and then 0.015 might be right here. So you trace them up, and you can't even really, with the naked eye, really distinguish this point from being on the red curve or the blue curve. I mean, it looks like they're on both curves. So that's the point of a linear approximation. All right, so this is a little fuzzy. I'm not sure why. So let's see, what else do they see here? Not much more. All right, so let's yeah, I mean, you can read through example 2. I'm not gonna go through it though. So that's all I want to see. There's some application of physics. Yeah. Yeah, sine of x is approximately equal to x, and this is important for like periodic motion, like if you have the pendulum, say, swinging about. Where did this go? Something's wrong with this. I lost my pen up here. Let me stop for a second, figure out what's going on with this. Feel free to skip this, of course. Oh, I can't. Oh, sorry. You can't minimize while you're recording. Oh, let's see, can I get... It's not working for some reason. All right, I think I got it, actually. Sorry about this. Share my screen. Okay, so yeah, so this is when you have a motion of the pendulum, it's gonna be periodic motion, and it's gonna be like some trig function. You know, periodic motion is always described by some trig function or some combination of trig functions. They really capture that periodicity because the functions themselves are periodic. But when your function is, when x is really close to 0, actually the sine function looks like this straight line y is equal to x. Anyways, what I want to get to is this differentials, and this is the part that's going to be really helpful for U sub when we get to the idea of U substitution. So what's the idea behind a differential? So differentials are roughly like changes in variables, whether they're independent or dependent. So you start with a function, um, and as it says here, we can actually reformulate linear approximations in terms of the in terms of differentials. So we start with a differentiable function f, and then we can talk about the differential dx is going to be itself a variable, and it can be thought about as some sort of usually thought of as some small change in x. So it's going to be, I mean, in the example we're going to look at, it's going to be just delta. We're going to take dx to be delta x, a small change in x. But dx is a variable, just treat it like that. It's like a variable x or y or z. So it's just a whole unit itself. Dx is a whole unit together. It's not like a product of d and x. It's a unit, a whole indivisible unit. The notation is indivisible, is what I mean. You can't break it up. So this can be taken in any real number, and given that, you can find the differential of y dy in terms of this right here. It's going to be dy is equal to f prime of x dx, and there's a lot of ways it can be reformulated using Leibniz notation. We could say that dy dx is equal to dy is equal to df dx times dx, or you can, because you know y is equal to f, you can say dy is equal to dy dx dx, or you have this over here, like as they say, if dx is non-zero, it's a variable, it's a number, it's a quantity, so you can divide both sides of this equation right here by it and obtain this. And so this is what is this said, this, as it says here, this is something we've seen before, and we can actually interpret this now as honest to God ratio. This is just a formal definition. It's just a formal definition. So given this variable dx, the differential of x, you can find the differential of y. So this is all very formal. This is just a formal definition. You can just take it as at face value if you want. But there's a lot of ways of rewriting this. But what does this mean geometrically? So the idea is that if you have a point on the curve, so you start with a function f of x, you have a point, this point P, and then you have some point nearby. So we'll probably take delta x to be small. So small number, small. Whoops. My computer is freezing for some reason. I don't know why. Yes, it's really annoying. There we go. So we're going to typically take this to be some small number. So then x plus delta x will be a point that's close to x itself. And then given that you can find the change in y, dy, it's just going to be the change in the function. So now what we have is the following setup right here. So we have the blue curve is our function, and we're going to just take dx to be the change, because dx is just any variable. It can take on any number, and so we can take it to be, in particular, this delta x. And then now what we have is the following. So we have x, and then we have x plus delta x, so some point that's close, and of course this is equal to x plus dx, the differential of x, so it's just a small change in x. And then you have dy, sorry, you have delta y is the change in the function, so it's in the y value of the function, the y values, I should say. So you have this point right here is Q, this point is P, and then um, delta y is this change right here in the y coordinates of the points P and Q, whereas dy is going to be the change in the point P and the y coordinates of P and R. So that's more or less what's going on geometrically with these differentials. But it's just a formal definition. Let's see, do we want to go through this example? This looks kind of tedious. I don't think it's going to be really illuminating. Um, so let me see. So dy. Yeah, as it says here, I guess I can read what this is saying. So it says dy represents the amount that the tangent line rises or falls above the curve, whereas delta y represents the amount the curve rises or falls. So it's like you have this point P, it can be viewed as a point on both the curve and the tangent line, because it is a point on the curve and the tangent line. And then you have this corresponding point over here that corresponds to changing x by delta x or dx a little bit. But then you can plug x dx into the line itself, and that will give you a point up here. And so it's like um the dy is going to be how much does the line rise above this point right here, whereas the or falls below, I guess, because delta x could be maybe be a negative number over here, probably not though. And then dy represents, sorry, delta y represents the how much the curve rises above this point. The curve itself rises above the point P. All right, let's see. Do we want to go through this example? I don't think so. It's just a bunch of tedious calculations. And then of course, well, okay, so one point is like you can take this difference right here, dy delta y, and this will be like how far off the line is from the curve. It'll like tell you how badly you approximate the curve. Of course, when this point Q is closer to the point P, that this difference right here will be smaller. And then they say here in the notation of differentials, this approximation right here can be written as follows, I guess. Okay, so they're doing that by taking dx. Well, okay, dy is equal to f prime of x dx. Oh yeah, and then taking, so if dx just is equal to x minus a, then of course when you can solve for x, it'll be equal to a plus dx, and then you can plug in, so now dy is going to be equal to f prime of a plus dx. I don't know if that's helpful though, times x minus a. I don't really see how they get that though, and why that's even interesting. Anyways, so that's all I wanted to say for in differentials. Not a whole lot, but just more or less give the definition. So I'm gonna pause for a moment.